Hello, so today we're going to be refactoring an SSE service in .NET, and this SSE service works, right? But it's 400-line mess with static dictionaries, magic strings everywhere, and it's basically untestable. So we're going to try to fix that today. So here's what we're kind of dealing with is like, it's one giant class doing everything from rate limiting to SSE formatting, database polling, event building, etc. Static mutable state for tracking streams, and it's pretty hard to test that. Magic strings like file completed, job failed, scattered throughout, and direct HTTP response manipulation everywhere. So throughout the original code, we had event type strings scattered everywhere, like file completed here, job failed there, heartbeat, error, etc. One typo and it can like easily break silently. And good luck, finding all the places you need to update if you rename an event. So a simple fix, we're just gonna create a static class with constants. We're gonna call it SseEventTypes and add all the string events into those as constant strings. And instead of having strings, we're gonna just use the SseEventTypes.file completed, job failed, etc. Next problem. SSE formatting logic was scattered throughout the service, mixing with business logic. Every event we sent meant manually writing headers, serializing JSON, flushing the stream, etc. So we extract an interface, call it ISseWriter, and we have first two methods, configure the response headers and write an event, and later we will add the retry interval too. Write event async is where the actual events get sent. First we serialize the data to JSON with camel case naming, since that's what our frontend expects. Then we write two lines, which is event colon the event type and data colon the JSON payload, followed by the two new lines, which then signals the end of the event per the SSE spec. When we flush the stream immediately, this is critical because without the flushing, the data sits in a buffer and the client doesn't see it until the buffer fills up. Configure response sets up all the SSE headers. Content type has to be text event stream, and that's what tells the browser that this is a service sent event connection. Cache control, no cache, because we're streaming real-time data and we don't want anything cached. Connection keep alive to maintain the persistent connection, and XSL buffering set to no, and this one is important if you're behind the Nginx, otherwise it will buffer your events and the client won't see them in real time. Okay, so let's see how we use this. First, register it as a singleton in program CS, since there's no state and just the static JSON options, and then inject it via dependency injection into our service constructor. And then now we can, delete the old send event async method entirely because we don't need it anymore, since now we have write event async from the writer. And same with setup SSE headers, we can replace them with configure response. And now we can just go through and replace every send event async call with SseWriter.write event async. The service no longer knows anything about SSE formatting, and when we write tests, we mock ISseWriter and then verify the right events were sent. Looking at our service, we're also writing the retry directive directly, and that hard-coded retry 5000 string, so we need to change that, and let's add that to the interface too. We're going to call it write retry async, which tells the client how many milliseconds to wait before attempting to reconnect if the connection drops. If the server goes down or network blips, the browser will automatically try to reconnect after this interval. And what we do is we send this once at the start of the stream, and now instead of writing raw SSE format strings after we have implemented it in our service, we can call it with write retry async. So next up is rate limiting, and before we had static dictionaries tracking user stream counts or trial loops with magic numbers, and our parameter is returning error messages as strings. First, instead of returning error messages as strings, we can define an enum. Let's call it rate limit result enum. And there are three possible outcomes: acquired, user limit exceeded, or service unavailable. And now the caller can use the switch expression and the compiler catches missing cases. Then we can create an options class, which can call it StreamRateLimiter options, and it can have two settings: max streams per user and max retries for the atomic update operation. We give them some sensible defaults and we can configure them from app settings.json. Now the interface. We can call it IStreamRateLimiter, and we expose the active stream count and max streams per user as properties for health checks and monitoring. Then two methods: try_acquire, that takes a user ID and returns our enum, and release, that takes a user ID and frees up a slot. For the implementation, in-memory stream limiter is a class that we can create, and we inject our options using the options pattern. We have a concurrent dictionary mapping user IDs to their current stream count, and an integer tracking total active streams across all users. Try acquire is where the thread safety matters. We loop up to max retries because we're doing optimistic concurrency. First, get the concurrent count for this user, so get or add, return 0 if they don't exist yet. If they're already at the limit, we return user limit exceeded immediately, and otherwise, we try to atomically update their count from current to current +1 using try update. This only succeeds if no other thread changed the value in between. If it fails, another thread beat us to it. So we loop and try again. Once we successfully update, we use interlog.increment on the active stream count, and this is atomic, so no race conditions. If we exhaust all retries without succeeding, something's very wrong and we return service unavailable. Release is the reverse, but we need to be careful not to go negative. So we use add or update with a lambda that only decrements if the count is above 0 and tracks whether we actually released anything. Only if we did release do we decrement the global active stream counter. This is registered as a singleton. It has to be because the state needs to persist across requests, and that's the whole point. If it was scoped, every request would get the fresh instance with empty dictionaries and rate limiting would never work. Now, if you're running multiple instances behind the load balancer, this in-memory approach won't be enough, obviously, and each instance has its own dictionary. So you'd swap it in a Redis-backed implementation instead, right? And that's just a different class implementing IStreamRateLimiter, and nothing else changes. We track the current scope, the DbContext, and when we last created them. So last piece, the database polling. In the original code, we had this streaming context class holding a DbContext, a service scope, and timestamps when to refresh them. It existed to work around async methods not allowing ref parameters. A code smell telling us this should be its own thing. So we extract IImportJobPoller. It's disposable since it owns a service scope, and we have two methods. Refresh context if needed, that takes a max age time span, and getJobAsync that fetches the job with its items. For the implementation, we inject ISeWriter because we need to create our own scopes, and we create them because our SSE stream can run for up to 30 minutes, polling every second. But a scope DbContext is tied to the HTTP request lifetime, and it's meant for quick request response cycles, so not long-running streams. If you use the request scope DbContext, it would accumulate track entities over hundreds of polls, and it would eat our memory and potentially return stale data. By creating our own short-lived scopes, we control the DbContext lifetime ourselves. We track the current scope, the DbContext, and when we last created them. Refresh context if needed checks how old our current scope is. If it's still fresh, we return early. Otherwise, we dispose the old scope if there is one. Create a new scope, resolve a fresh DbContext from it, and update our timestamp. We refresh every 30 seconds, which is frequent enough to avoid stale data. Infrequent enough to, not hammer the DI container. Dispose cleans up the scope, which disposes the DbContext with it. GetJobAsync is pretty straightforward, just the EF query. We do as no tracking since we're only reading, and include the items, filter by job ID and user ID for authorization, and we throw if someone calls this before refresh context if needed. We fail fast instead of a null reference somewhere deep in the service, we create the poller with a using statement, so it's disposed when the stream ends. Inside the polling loop, we call refresh context if needed with our max age constant before each query, and the poller handles all the scope lifecycle complexity, and the service just asks for the job. Alrighty, so let's recap what we did. We took a 400-line monolithic SSE service and broke it into focused and testable pieces. We created our writer, our poller, and our rate limiter, and the main service now just orchestrates these pieces, and each one can be a unit tested in isolation, mocked when testing the service, and swap out for different implementations if needed. Next video, we'll implement the inbox pattern with mass transit for processing our import jobs, and that's what actually triggers the file completion events this SSE service is streaming. And then we can test the whole flow end-to-end, upload some PDFs, watch the event stream in real time, and see everything working together. And we can try turning off the RabbitMQ service and see what happens with the outbox pattern from the last video, and so on and so on. So yeah, thank you for watching. I will see you in the next one. Please, if you like this content, like and subscribe, and keep keep in mind I'm still learning, and hopefully we can get better together. If you want to comment anything, tell me maybe if something's wrong, there is an obvious error, please do let me know. So thank you, bye.